different from as I began to build this map from the sedimentary sequence which fills an area that we call the Michigan Basin. It's hard to imagine what's underground from the surface, but as we began to, through seismic work and through drilling, began to explore this area over the decades, this picture has been significantly sort of filled out and colored. When we talk about these ores, the iron ores, many of you probably wonder what's so special about them. Well, iron doesn't like to be at the surface of the earth and moved by water because it likes to rust. I have an old Mercedes that my parents gave me, and I can tell you that it sat in my backyard, and every year I'd take a broom, and I think I'm back down only to a couple plastic pieces that are left behind. So iron basically likes to rust, and so to actually make a major deposit of iron, it's difficult because you can't dissolve that iron in water, except under very, very unusual situations. And during the early evolution of our Earth, our atmosphere lacked a lot of oxygen, which meant our oceans were full of dissolved iron, of what we call a reduced state of iron. As photosynthesis by early life on our Earth began to raise that oxygen level, we began to see the precipitation of that iron in massive deposits, which are not only here, but worldwide. I work out in Wyoming a lot at the University of Michigan's Camp Davis, our field station. And in the Southern Wind Rivers, there's a rock body of this same age. And we call these the banded iron formations because they represent thick accumulations of iron oxides, something magnetite primarily, interlayered with chert, which is essentially quartz. But this is material that was formed on the seafloor from ocean water that at that time was full of dissolved iron. So this represents a remnant of what existed on a global scale. And there are other places these days that actually have a lot more of this resource left. We still have iron ore in Upper Michigan that can be mined. It's a commodity. We'll see that much of the mining potential and resource exploitation in Michigan is really driven by the market. There are places in the world now that it's much easier, much less expensive to actually mine that material. So until iron becomes a limiting resource, I wouldn't expect, and Hal, is that reasonable sort of evaluation?
Yeah, I think so.
Yeah.
Economically.
It's just not economically possible right now. But in fact, it includes this broad area of iron stone deposits, of banded iron formations throughout this region. Now, interestingly, about 1 billion years ago, we've all heard about the supercontinents that formed through time, the last of which was about 250 million years ago when we were really close to Europe and South America and Africa, where everything was clustered together into a supercontinent called Pangaea. During that collision, of course, we lifted up the Appalachians and the mountains in parts of Africa and across the globe. Well, prior to that, there was another supercontinent called Rodinia, where all of the continents essentially had merged together into one mass. But the general cycle of continental drift is one that things come together. I guess it's sort of like politics. Things sort of come together and then they seem to fracture and rift apart. And within this part of the world, we in fact developed what's called the mid-continental rift system. And rifting essentially is that process of breaking a supercontinent apart. And associated with rifting is a massive amount of eruptive phases. In other words, material which is coming from deeper in the earth and is erupted and brought close to the surface. It's within that kind of rock that many of our mineral resources are ultimately derived. Through processes of water interacting with these igneous rocks, we leach that material out and move it and deposit it in veins or disseminate it through shales. And it is this event, or it's this event of rifting that in fact really sets the stage for the evolution of Michigan for the next, from 1 billion years ago up until today. And in fact, when these volcanic rocks erupted on the surface, they produced a very distinctive type of deposit. In this case, these are rhyolites, basalts. igneous rocks, which then were weathered and produced coarse deposits of gravels. If I showed you a close-up of that, you can see individual pebbles in here. But interestingly, the hot fluids associated with these eruptions also moved a lot of copper. And so when we talk about, you know, Copper Harbor, the reason why it's Copper Harbor is because in these rocks there's an abundance of native copper. And native copper is the nicest to mine if you can do it, because it avoids all of those potential contaminants, sulfides, which ultimately we have to worry about how they're processed both in the mining process, because if they oxidize, they produce an acid which can create ecological damage. When they're processed in terms of smelting, produce sulfur dioxide, which ultimately creates acid rain. So these deposits are still in existence. They closed White Pine Mine, I think, during my tenure at Michigan, which is 30 years. Probably they closed in the early 80s or something.
95.
95. And those are flooded now, I assume. Yeah. But again, these deposits still have copper in them. We still have copper in northern Michigan in the Keweenaw. Again, it's commodity price driven. This is not copper. There are enough big mines in the world that can handle this. And just to point out, here's White Pine down here. And Copper Harbor, for which this rock is actually named, is in fact located in this northern part. And when we began to look at some of the new prospects in some conversations I've had here, it sounds like in the next year, the Eagle Mine will open up. This is also a copper, but what drives this mine is that it also has significant resources in terms of nickel and some rarer elements like palladium and platinum and gold, all of which they can recover from this deposit. So at least at the present, this is an economically feasible exploitation target. Again, the process by which this formed is essentially the eruption of volcanic rocks and then the subsequent migration of these ore flows. But I said that this sort of sets the stage for the long-term history of Michigan. And it sets the stage because it will also define the process by which we began to sink into the earth, a process called subsidence. We create what's called the Michigan Basin region. Oops, I'm a little ahead of myself. But this is just let me go through a couple things first. I talked about the surface veneer. This is a map of prepared by and published by the state geologists in the Department of Environmental Quality. And these are all available online. But this shows you all of the gravel and sand deposits, the Pleistocene, the last 10,000-year deposits as they're distributed across Michigan. The topography that we see here in Michigan is largely produced by these deposits. This is an exposure in one of the Killen's Quarry, which is actually in Ann Arbor, but several years ago. My colleague here has even gotten bigger. That's how I know that it was a few years back. It's Bruce Wilkinson, excellent geologist, taught me a lot as a young geologist. But I said that when we began to look at detail to Michigan, what we're going to see is that when we add the distribution of rocks underneath this cover of gravel, in fact, it shows some very distinct patterns. And those of you that are not geologists or think in terms of structure or the shape of things in 3 dimensions, I think you can see that we've got sort of a series of bullseyes. And what that represents essentially is what you would expect if you cut through a series of rocks which are slightly dipping on the margins and dip down into a deeper basin. And so it's this Michigan Basin and the sedimentary sequence which is deposited in it, which really provides us with not a metallic ore resource, but rather primarily such things as the hydrocarbons and such things as the salt. And it's the evolution of not only the Michigan Basin, but also of the Earth as a whole, which led to variations in the kinds of rocks that are formed here. There are times when across the globe, we see very organic, rich black shales produced. For example, across North America today, in Michigan, we have a shale called the Antrim Formation. It's very similar to the New Albany. It's very similar to the Chattanooga. It's very similar to black shales I've observed in parts of Europe. It's very similar to shales I've worked on in Alberta, something called the Lohmann, which is an old but very, very distinctive black shale. And so this sedimentary sequence then has a diversity of rock representing a diversity of environments when it was formed, and it's within those environments that we have such resources as the storage of carbon. Storage of carbon, which subsequently can modify into usable hydrocarbons. If we look across the country today, in fact, we see that there are a number of such basins. And so here, if we think of a basin as a downwarp, I always say geologists are not great with words, so we usually describe things pretty simply. A basin, like a wash basin. A wash basin, we have a major basin, Michigan Basin, there's the Illinois Basin, there's the Williston Basin, the Appalachian Basin. Basins are available throughout our country, and it will see later that each of these basins has their own potential for hydrocarbon development. In the case of Michigan, again, I said that it was really a process initiated in part by this rifting event. As we began to pull things apart, rift them apart, you thin them. You put heat in them. They lift up, they thin. As they began to cool, they began to subside. And in fact, in an old cross-section, to give you a sense of what's happened here, this is the old crust that has been thinned and broken, and as it cools, it subsides, much the way a hot air balloon, as it cools without hot gas, begins to sink in the air. In fact, our basin, the rocks which make up our basin, begin to subside into what we call the asthenosphere, the plastic outer part of our deep earth. In fact, if we look at the spectrum of this, and I don't know why I put this animation in, but I thought it would keep people awake. I usually have to worry about students with earphones in. None of you do, but except for actually being able to hear me. But in fact, if we look at a general cross-section, we have on the order of about 16,000 feet of these sediments preserved within our basin. And again, these range over a time period of about 500 million years in time. Up to about, well, the youngest rocks that are exposed, I'm going to say to an extent, are on the order of about 250. So this represents about 250 million years of history, of Earth history. Again, as I began to look at this in detail, again, we can see the pattern, this pattern of concentric sort of layers, the youngest being in the middle. That's what we'd expect, downward. Youngest rocks in this area, for example, that are easily exposed are of something we call the Pennsylvanian age, also called the Carboniferous. Why do you think, I always like to ask questions, Diane, why do you think we would call a bunch of rocks Carboniferous? In carbon. And in fact, this is an interval in geologic time on a global scale where we see vast quantities of carbon, primarily as coal. And in this state, there's been a tremendous amount of coal production in the past. I don't know whether or not we still mine coal. Most of it's being done in Ohio and the Appalachians.
Last coal mine in operation was 1955.
Okay, so I was 5 years old. Okay. Okay, I'm older than I look. But in fact, we do have a number of resources in here that are in the subsurface that are not part of that glacial environment. But in fact, we have limestones. And limestones continue, if you ever go down toward Ohio, you'll see in the distance around Dundee major smokestacks, production of cement. Much of the easily accessible shallow mining, I guess a lot of that's been done. I know that up around Petoskey, there were, that limestone was essentially mined out. But in fact, we still do have limestones as part of our natural resource. I mentioned that salt's also important. When we began to think in terms of geologic time, and I recognize I didn't put time on this, this layer up here is this glacial debris. Depth of this depends on where you are in the basin, but somewhere on the order can be as much as 16,000 feet. And it represents, again, from about 500 million years, a up to, again, 10,000. But what I want to point out is in this interval in here,